recording. The floor is yours.
Okay, yeah. Can I begin? Okay.
Yes, go ahead. Go ahead.
Okay. Hello, Professor Eleni, and hi everyone. I'm Cheng-Geng Huang. For convenience, you can call me Alex. I'm a research fellow in Module 1.3 and 3.2 of FRS, led by respected Professor Eleni. It's really a great honor and opportunity for me to give you a presentation about intelligent transfer fault prognosis under cross-domain scenarios. This work is in collaboration with Wei Wenpeng in Sun Yat-sen University and Zisen Ye, as well as LC Tang in NUS. I will present my work from the following 4 points. Firstly, I will give a brief introduction about the research background and the motivation of this work. Prognostic and health management is a computation-based framework that use physical knowledge and information and condition monitoring data of industrial systems, such as power plants and civil infrastructure, such as bridge structure, to enable detecting anomalies, diagnosing faults and degradation states, further predicting the evolution of the degradation to the failure. The outcomes of PHM task can be used to support condition-based and predictive maintenance decisions for the efficient, reliable, and safe operations of critical industrial systems and components. This work focus on fault prognostic task, which is essentially belonging to a regression issue. Fault prognosis is actually an engineering discipline focused on predicting the time at which a system or a component will no longer perform its intended function. In order to achieve the fault prognostic purpose, traditional methods and deep learning-based methods are widely used. For traditional methodology, feature extraction is a critical and challenge step. Specifically, human ingenuity and prior knowledge are needed to design fault future state. However, when dealing with a new prognostic task, the future extraction algorithm may need to redesign. So, for traditional fault prognostic methods, handcrafted future extraction is a time-consuming and labor-intensive step. Compared with traditional prognostic methods, deep learning-based prognostic framework is endured with powerful future extraction and nonlinear function fitting capabilities. The discriminative and informative high-level features can be adaptively extracted through the sophisticated deep learning network in an end-to-end manner. However, for deep learning based fault prognostic methodology, there are still 2 critical challenges remains to be unsolved. Specifically, massive labeled training data are required to train deep learning network in a supervised framework to guarantee the prognostic accuracy and the generalization capacity. However, the connection of the massive labeled data is very challenging issue due to time, economic risk, and even safety concerns. Secondly, classical deep learning-based methods are unable to handle prognostic uncertainty and tell us how much confidence it can have on its life predictions. This issue can be significantly important for some mission critical and safety critical systems, such as some critical components or subsystems in nuclear plants and aerospace applications. For example, for a critical rotating machineries in a nuclear power plant, the deep learning based method estimate that there are about 3 years remaining to be repaired. However, this result is not sufficiently informative for maintenance actions because it might be from 2.9 to 3.1 or 0 to 6, yeah, with 95 confidence. So that's the reason why we need the prognostic uncertainty information. And for the research challenge of the massive labeled training data collection, actually in the real industrial applications, similar industrial products are widely used in various engineering applications, such as bearings in high-speed train, wind turbine, and automobile. However, the failure modes of these products sometimes are similar, such as for rolling bearings. Yeah, the failure modes are inner or outer race wear, cage or outer race rupture, and so on. And there is also another interesting observations needed to be mentioned, that the labeled condition monitoring data in real case is scarce and always truncated. However, the condition monitoring data in laboratory are massive. Yeah, we can and can be effectively labeled through some experiments, such as run-to failure, accelerated degradation experiments. So therefore, it is quite natural to consider that, can we transfer the shared fault prognostic knowledge of similar products across different scenarios? Yeah, that's a very interesting questions. Such as we can, such as cross different operating conditions within same products, or even across heterogeneous machines. And that's our research topic, cross-domain transfer fault prognostic. Meanwhile, as mentioned before, how to quantify the prognostic uncertainty for transfer fault prognostic task. To be honest, this research topic is quite a challenging topic. So I will investigate this issue in a divide and rule manner. Next, I will briefly introduce my proposed methodology. Firstly, I will present the problem formulation. Let us recall that the general characteristic of traditional fault prognostic scenario and the concerned transfer fault prognostic scenario. For the first case, we often assume that identical machines operate under similar conditions, which lead to similar data distribution, and thus is beneficial to developing the prognostic model. This situation can refer to the first figures. As you can see, there are 7 bearings. They are, the same bearings working under identical condition. So the data distribution is in similar patterns. Yeah, they are almost the same. The PDF, this is the probability density function of some specific features. So the pattern of the PDF of the future is similar pattern. However, this is a strong assumption, which is unrealistic and even unpractical in real industrial. As a result, this severely restrict the collection of labeled training or test data, further increase the model deployment cost in real cases, where the accuracy and the generalization capability is in high priority. On the other hand, for the second case, for the second scenario, we only assume that similar but heterogeneous machines work under different conditions. I mean, the working conditions maybe can be mild, moderate, or harsh conditions accordingly. This scenario greatly enhances the application flexibility in real industrial and also breaks through the bottleneck of the labeled data dynamo, reduce the model deployment cost. However, the other side of the coin is that the data distribution in this scenario are significantly different, such as in the second finger, yeah, they are working under different operating conditions. So the PDF pattern is a little different. And the third finger is about heterogeneous machines working under different operating conditions. Yeah, the PDF is significantly different. So that's an issue. This topic need to resolve. Okay, let's take a step further and formalize the concerned transfer fault prognostic issue in the transfer learning framework. Let's denote source domain as DS, target domain as DT, and the future space this X. Specifically in the source domain, the labeled sample size, we just assume that the labeled sample size is big enough to train a satisfactory deep learning based model in a source supervised learning manner. By contrast, in the target domain, the labeled sample size is very small or even near to zero. However, there are some unlabeled samples we can use due to preventive maintenance or repair actions. Finally, the future space in source and target domains are assumed to be same. However, due to cross-domain issues, they differ in data distribution. That is, distribution discrepancy exists in their marginal distribution. Our research objective is to build a cross-domain fault prognostic function which can generalize well in target domain by utilizing DS and DT. The core idea is to utilize deep learning model to extract the domain invariant features, thus to reduce the distribution discrepancy between the source and the target domains. More specific, the unsupervised domain adaptation-based methodology is adopted to address the cross-domain issue without any labeled training data in target domain. I guess everyone in the group supervised by Professor Eleni might have a solid theoretical foundation about deep learning. So I will just introduce some basics of deep learning. Generally, there are three critical steps in deep learning methodology. In the first step, we should define a lice model. This is relevant to deep learning network architecture. In the second step, we should define an appropriate strategy to determine the objective of the model. This is relevant to the loss function definition. In the final step, we should choose an efficient optimization algorithm to pick the best model. This is relevant to stochastic optimization algorithm and its related hyperparameter selection, and so on. Following the aforementioned three steps in basics of deep learning, we can also draw a general sketch of deep transfer learning, which also includes three important parts. In the first part, we should design an appropriate deep learning architecture to represent the distribution discrepancy of the hidden features from both source and target domains. In the second part, we should define an appropriate loss function to measure objectives of interests such as regression loss and the distribution discrepancy loss, and so on. In the third part, we can minimize the training objectives described in the second part to achieve the cross-domain prognostic task. Specifically, let's begin with the first part, which is network architecture. In this work, we design a very simple yet effective network architecture where 3 modules are included in the proposed network. They are filter, extractor, and remain useful life. This is life predictor and the domain adapter. Specifically, for fault filter extractor, we integrate multi-layer perception and the deep convolution neural network to design a dual branch network. Multi-layer perception is used to this MLP. MLP is used to extract the features hidden in the one-dimensional time series-based input data. By contrast, deep learning, deep convolutional neural network is used to extract features hidden in two-dimensional image-based time frequency representations. Then these two hidden high-level features are concatenated together to characterize the discriminative hidden features. Next, for the life predictor module, which is used to achieve the fault prognostic task. Finally, for domain adapter, this module is designed for quantifying the distribution gaps between source and target domains and will be elaborated in the next page. For domain adapter, we can use various domain adaptation techniques to measure the distribution discrepancy exists between source and target domains. I will briefly introduce 2 widely utilized domain adaptation techniques, which are this discrepancy-based technique and the domain adversarial training-based technique. Specifically, for distribution-based technique, an explicit quantitative metric is used to calculate the distribution discrepancy between source and target domains. Among different metrics, the maximum mean discrepancy, which is MMD, is a classical way to compute the distribution discrepancy, which is as shown in the following equation. Next, domain adversarial training-based technique, which can implicitly measure the cross-domain distribution discrepancy, and the core idea lies in the philosophy of generative adversarial network, which is GAIN. Also, as shown in the figure, the future extractor learn indistinguishable high-level representations from both domains to deceive the domain discriminator. Meanwhile, the domain discriminator aims to differentiate the fault features of target domain from that of the source domain and further classify the specific domain labels. This adversarial training process can be formalized as the following equation. Specifically, the cross entropy loss function is utilized for the loss function. Finally, we can formalize the optimization objectives of the concerned transfer fault prognostic model. The optimization objectives includes 2 parts, which are the life prediction loss (LP) and the domain adaptation loss (ALD). After that, the add-on optimizer can be used to complete network update, and the network parameters of filter, extractor, life predictor, and the domain updater can be optimized. Although the transfer fault prognostic task is achieved by combining deep learning and transfer learning, however, the the proposed model is still a deterministic network structure, which can only output a point estimation. So, to address the issue of prognostic uncertainty quantification, the proposed deep transfer learning based network is further extended in Bayesian deep learning framework. Due to the limited time, I will present some fundamental basics and the implementation clues of Bayesian deep learning methodology. Actually, a Bayesian deep learning model is fundamentally a probabilistic extension of the classical deep learning model. Network topology of the classical model is preserved for inheriting its modularity and scalability. What's more, the model parameters of this classical model are treated as random variables for uncertainty quantification through probability distribution. According to the Bayes theory, the nerd posterior distribution of the model parameter, which is denoted by omega, and given the training dataset x, y, can be briefly given as the following equation. However, for the sophisticated learning deep neural network architecture and the high-dimensional input data, the posterior distribution is often intractable. Therefore, a probability distribution family Q phi omega parameterized by phi is chosen as a variational distribution family to approximate the posterior distribution. To obtain an optimal variation distribution, KL divergence is used to compute the similarity of these two distributions, which can be written as the following equation. Then we can substitute the posterior distribution into this KL divergence equation, which is this equation. Yeah, we can substitute the posterior distribution into KL equation, and we can obtain this following complex equation. Specifically, the first term of the right side of the equation is the KL divergence, a divergence between Q phi omega and P omega. Minimizing this term will result in the variational distribution family being near to prior distribution. This P omega is prior distribution of the network. And the second term can be denoted. This is Q phi omega. Yeah, this is variation distribution, and the P omega is prior distribution. And the second term can be denoted as the expected log likelihood of this term, and the max. And as you can see, there is a minus sign. So maximizing this term will contribute the variational distribution family to fully explain the training dataset through the developed sophisticated deep neural network. The last term can be regarded as a constant term because there is independent of the independent of phi, so it's a constant term. So we can delete it. As everyone knows that the most deep learning models is trained in a mini-batch based optimization method. Similarly, mini-batch based optimization method is also utilized in Bayesian deep learning methodology to reduce considerable computation resources and KL divergence between the variation distribution Q phi omega and the posterior distribution given x and y can also rewrite as the following formula, in a mini-batch fashion. At last, a stochastic optimizer such as the Adam optimizer can be utilized to learn a local optimal phi star, which is also an optimal to KL divergence between the variation distribution and the posterior distribution given x and y. And it is proved that implementing variational inference with Q phi omega is essentially equivalent to implement dropout in deep neural network. To be honest, the process of the proof is quite complex and elusive. Interested listener can be referred to the GAL PDF thesis. However, from the implementation perspective of Bayesian deep learning, it is unbelievable simple and easy. The deep learning neural network with dropouts are enabled both in model training stage and model testing stage, which can be considered as a Bayesian deep neural network. It's very simple and easy. Finally, the most important question is that how do we indeed quantify the prognostic confidence interval? Honestly, it is also quite simple and easy. All thing we should do is just during model testing stage, multiple estimations with dropouts enabled can be implemented to obtain a group of posterior distribution, which can be utilized to quantify the confidence interval of the testing samples in target domain. Actually, the theory and the engineering applications of Bayesian deep learning is still in a period of rapid development. The concerned Bayesian deep learning methodology is simple and the fundamental version. So if you are interested in this topic, please follow the research work conducted by Professor Gale in University of Oxford. Next, we will thoroughly investigate the proposed methodology through a case study. Okay, I'll drink some water. The first case study is about cross-condition transfer fault prognostic issue. In this scenario, two rolling variance datasets are adopted to investigate the proposed methodology. Specifically, the test beds of these two variant datasets are shown in the following figures, and the description of the experimental details are summarized in the right table. Generally, for XJTU SY variant dataset, a total of 15 rolling variants are subjected to run two-failure degradation test under 3 different operating conditions. Similarly, for prognosis for the second dataset, there are a total of 17 run to failure raw vibration signals that are collected in different operating conditions. As shown in the left table, the operating conditions are mainly controlled by radial load and the rotating speed. So the different operating conditions can be generated under different combination of the load and the speed. In order to validate the effectiveness of the proposed method, we create 7 different transfer fault prognostic tasks. Let's take task 1 as an example. The variance in operating conditions 1 is chosen as the source domain. By contrast, the variance in the operating condition 2 is utilized as the target domain, and the labeled dataset as well as the unlabeled dataset and the testing variance are shown in the right table. Okay, this is relevant to the operating conditions. So And these are 7 created tasks. For the implementation of the proposed method, we first analyze the vibration signals from 2 acceleration sensors and further extracted 2-dimensional image-based time frequency representations. And this feature is based on is based on CWT, which is continuous wavelet transfer algorithm. And we also extract 1-dimensional time series-based features, a total of 32 different features, as shown in the figure, are extracted. After the primary feature extraction, we feed these heterogeneous input features into the proposed dual branch-based network. Note that the domain adversarial training is adopted in this scenario to tackle the issue of distribution gaps in both domains. What's more, a Bayesian neural network is not considered in this case study. We only investigate the effect of deep transfer learning. Firstly, we conduct ablation study of the proposed dual branch network with domain adaptation module. The comparative models are MLP DA model, which only takes 1-dimensional time series-based features as model inputs, and the DCN, which is a deep convolutional neural network, and the DA module takes 2-dimensional image-based features as model inputs. However, for the third and the fourth comparative models, the same dual branch network architecture is adopted in the feature extractor. However, the domain adaptation module is not included in these 2 comparative models. Specifically, for the third comparative model, only pre-training is conducted in source domain, and the model testing is directly achieved on target domain. As for the first comparative model, traditional model training and testing, conducted in target domain. And the performance results for transfer fault prognostic task 1 to task 3, is shown in the right table. As can be seen from the table, that the proposed method achieves the best prediction result in most tasks. Therefore, it can be observed that the proposed dual branch network structure can simultaneously integrate 2-channel heterogeneous input features to enhance the transfer fault prognostic accuracy. Next, we will investigate the effective of the integrated domain adversarial module for the aforementioned 3 transfer task. In the figure, the high-level fused representations are visualized through TSNE technique. The dimension reduction results are shown in figure. The different color gradient is used to denote the involution of the bearings degradation. As you can see from the figure, that there exists significant distribution discrepancy between the source and the target bearings for the model without a domain adversarial module, which reduce the transfer fault prognostic accuracy as shown in the right table. Note that in the right figure, the prognostic model with domain adversarial module can align effectively the high-level features in source and target domain, thus to improve the accuracy as shown in the right table. So this figure is for the task 1, and this figure is for the task 2. Similar patterns, similar results can be found, and for the task 3, as you can see, similar patterns. Finally, we also investigate the influence of unlabeled sample size in target domain. We present the ring cloud plot of RMC and MAE over 30 repeated runs under different proportion of the unlabeled target sample size for task 4 and task 5. it can be observed from the figure that the proposed model is robust to the unlabeled target sample size, even with a very low proportion unlabeled data. Yeah, we can obtain a nice accuracy. Finally, we also compare the proposed method with other existing method, which also validates the effectiveness of the proposed method. And in the next scenario, we investigate a more challenging issue, which is cross-machine transfer fault prognostic issue. Similarly, we also adopted the aforementioned two datasets. However, in this scenario, we want to achieve bi-directional transfer fault prognostic between these two different bearing datasets. These two open source datasets differ a lot in operating conditions, tested bearing specifications, and the measurement setting, such as from this table, you can see they have different sensor table, sampling duration, and the sampling interval. As you can see from this table, the operating condition, yeah, is also very different. For the first data set, the operating conditions is mild, and the second is harsh. Also from the bearings, yeah, from the bearings, they are also significantly different, such as the rolling bearings in the first experiment is much smaller than the second one, and the number of the rolling elements, diameter of the inner and outer rays, as well as the bearing mean diameter are significantly so different. So in this scenario, we assume that we have some labeled training dataset in the first experiment platform, and we want to achieve transfer fault prognostic of bearings in the second experiment. So this is quite a challenging issue. In order to validate the proposed method, we create 10 bidirectional transfer fault prognostic tasks, as shown in these three tables. Similar to the first scenario, we first analyze the vibration signals from the sensors and extracted the similar input features and feed into the proposed network. Note that the multi-corner maximum mean discrepancy metric, which is MMD, is utilized to tackle the issue of distribution gaps exists in both domains. And in this scenario, Bayesian neural network with MC dropout is adopted in this case study to quantify the prognostic confidence interval. Specifically, the dropouts is imposed in some specific layers, such as in some fully connected layers and convolutional layers during both model training and the testing stage. So from implementation perspective, yeah, the Bayesian deep learning is quite simple and easy. Just impose dropout during model training and testing. In this part, we analyze the robustness of the dual branch network to the noisy environment, which is quite common in real industrial. The comparison of transfer fault prognostic accuracy obtained by three methods for the two tasks are given in the left finger. As you can see from this finger that the proposed method is robust to different level of signal to noise ratios. Therefore, integrating one-dimensional time series features and the two-dimensional time frequency spectrum features into the proposed dual branch network is beneficial to improve the model's ability to resist the noise. What's more, we also investigate the confidence interval quantification result, as you can see from the right finger. However, the confidence interval quantification result is not very is undesirable. Only a small portion of actual values are included in 90% confidence interval. Yeah, we will do more work on this point. Yeah. And at last, we also conduct performance comparison with other existing methods on 10 bidirectional tasks. The result is shown in the following tables. It can be concluded that the proposed method outperforms the comparative method in most tasks and achieves significantly better transfer vote accuracy in 8 tasks among 10 tasks. Besides that, the proposed method also achieves comparable accuracy on the rest 2 tasks. Finally, I will draw conclusions of this study. Firstly, a transfer fault prognostic issue, including cross condition and cross machine, are considered in this study. Secondly, the significant distribution discrepancy issue existing in cross-domain fault prognostic is addressed through integrating transfer learning and deep learning framework. Finally, the prognostic uncertainty is quantified through MC dropout in a Bayesian deep learning framework, which deserves further study to refine the computation results. For my ongoing research, I'm conducting the distributed learning in federated learning implementation paradigm. Furthermore, resilient federated transfer learning under malicious clients and several attacks is also my another interesting research. Okay, thanks a lot for your patient listening. Thanks again for the invitation of Professor Elani. It's really a great honor for me and my collaborators. Okay, is there any questions? I will try my best to answer your questions.